Hello. I want to talk a little bit about quantum AI and quantum computing in the way that I actually understand them and try to demystify a lot of things that are being said in our industry and connect it to the reality of 2026. This video will not be that much about quantum physics or quantum logic. It will be mostly a computing person's point of view around quantum and quantum AI and the state of things as of today. Please bear with me. So the first thing to say is, what is quantum computing? Well, honestly speaking, from the computing point of view, we are still talking about computing, meaning that we have bits and we have gates and we do some stuff on those bits and we get some output. But the difference is, instead of having classical bits that are kind of like coin, that they have 0 or 1, head or tail, we are talking about quantum bits, the ket thingy that you see here, which can be in the superposition mode, meaning that they're mostly like a spinning coin as opposed to a coin that is landed on head or tail. And that's actually useful for some use cases, but for a lot of use cases it's kind of confusing, right? Like you need to observe to see what is the state of the thing. And instead of having and or and those kind of things, we need to now work with different gates, and they cannot do exactly the way that a classical computing machine works, and they still have probability and we're dealing with probability, but we can, using a concept called interference, which I will talk about in the next slide, we can get these machines to give us some good results, which is very, very important to understand. And that is very interesting because we are changing the paradigm altogether. 3 keywords about quantum that are very cool. One is superposition, the coin that is moving and it's not one thing at any moment, and you need to observe it to see what it is. The second thing is entanglement is the idea that you can link 2 qubits together in a way that looking at one tells you what is the other one. Talk with your local physicist. They will explain to you why we cannot use this concept to build a network that is faster than the speed of light. Unfortunately, having said that, it's super cool that these 2 qubits can be as far as possible from each other, and you can still read the information on one of them and figure out what is the information on the other one. Interference is mostly working like noise cancellation. So on these machines, in order to get the probability of the right answer higher, you're constantly using interference to wipe out the wrong answers and errors. That's the way that we are manipulating the system. And that's where things get interesting. So one key thing, if you only remember one thing from this video, if you manage to sit down whatever I'm saying and listen to it, is a GPU is like a bulldozer for matrix math. A quantum computer is like a tuning fork that we constantly try to use interference and other tricks to make sure that we get to the right answer. Fundamentally different paradigms. What that means is you cannot actually run models that require a lot of parallelization like a transformer on a quantum machine. It's just not going to work. It is an insane proposition, and I'll explain that a bit more. There's another myth which I kind of like to be true, but it's not, and that is quantum machine is so powerful that can try a lot of things at once. In reality, that's not true. In reality, for us to get to the right answer, you need to have using interference all the time, you need to use all the tricks, and to be honest, there's always a probability of giving us the wrong answer just because of observation problem. I'm like a party pooper here, but that's not actually how quantum machines work at all. When it comes to the AI, when it comes to the classical AI, and I want to be honest, there might be another class and category of AI that comes out one day, and in that case, we don't need to worry about this thing. There are 3 key problems with quantum. One, matrix. GPUs are fantastic in doing matrix math, multiplication, manipulation, all those kind of things. But it doesn't exist. Quantum machines cannot do that. They're not even in the same ballpark. Data loading in quantum machine is super harsh and hard. Honestly, it's impossible to, even if we had quantum machines with enough qubits to have a small model running on them, just loading the data is insanely hard. And dequantization is another issue. A lot of clever classical algorithms that we used to think that are really, really well suited to run on quantum, when people actually took them to large enough classical machine outperformed them. Turns out that the value was in the algorithm rather than the way that they were being computed on quantum. And this became a phenomenon because a lot of these interesting findings of previous decades are now being negated. I think we are in a vacuum tube era stage of quantum computing, while we are in the iPhone era of like classical computing. So the two are categorically different things to compare. It takes a lot of time for quantum machines to become something useful, not even punch card state. I said vacuum tube era for a reason, because everything is finicky and noise is huge and error is still very, very much there. So Jensen Huang said, if somebody gave you the option of 10, 20 or 30, I think if you say in 10 years we will have quantum machines that are very useful, you're being kind of over optimistic. If you say 30 years, you're kind of being too harsh. The speed of change, I think in 20 years is what he said. I think it makes a lot of, I echo the same thing. I think this is probably the right timeline to think about these things. Now, that said, a lot of things that will happen in quantum machine learning will be a hybrid loop between classical machine learning and GPUs and quantum. Pharma and drug discovery is a very interesting idea, because I think because a lot of the phenomena that we are trying to simulate in the machine learning for pharma are actually quantum phenomenon on the molecular level, quantum machines will be very well suited to do those things. Financial and risk modeling will be very interesting use case as well. There are a lot of POCs out there that show that with small quantum machine we can do these things. But the problem seems to be that we haven't yet built very large quantum machines to run these things meaningfully. And for the classical AI, there's a bigger problem. Most of the gradient descent and most of deep learning models rely on finding ways to not fall into the to the barren plateaus, right? Like in the stage that they cannot find the path forward. Given the problem of observing quantum bits and changes that they do whenever you observe them, they are really, really hard things. Even if we had these large quantum machines, we still won't be able to do a lot deep learning on them in a meaningful way. I'm just trying to drive this home that quantum machine learning will be fundamentally different strain of machine learning at some point. Shor's algorithm is the one thing that created a lot of noise. It has been out since 1994. Peter Shor showed that in calculating huge prime numbers and multiplying huge numbers, you can actually, and finding the factorization of them, you can actually use quantum machines to do these things much, much faster. Things that we used to say takes billions of years can be done in hours or days with these things. And this is a problem because of the probability of actually getting good machines out there very soon. But to be honest, we still don't have enough qubits to run these things. So that's not something that people can do. That's why most people are doing harvest and wait. A lot of state actors and non-state actors have started, because storage is very cheap. They're storing a lot of encrypted data with the hope that one day they can actually open it up and read it. And that day is very soon because of Shor's algorithm. And there is Mosca's inequality, which is the idea that says that if you're a CTO, if you're a CEO, and if you have a data that you need to have the confidentiality, maybe weights of your transformer, whatever, you need to think about Q day and post quantum day, and make sure that you understand that the current encryption mechanisms will not be that useful in a decade or a decade and a half time. And that's why US government and many other organizations are now talking about post-quantum TLS and post-quantum encryption. And that, I think, is a very real thing, and you need to think about it. Some regulations are now asking you to do so, so it's not at all a hypothetical game. And also in some cases you need to think about the cost of computing and re-encrypting stuff with post-quantum TLS or similar kind of stuff. Thank you very much for listening to me.